Hi, everyone. We're jumping into chapter 12 today, and we're going right to section 12.5. So we're skipping a lot of initial content in the chapter. If time allows it all, we'll revisit and touch on some of the highlights there. But 12.5 is standalone and covers the important concept of correlation. In fact, some of you may remember one of the last topics we were working on right before spring break was dealing with multiple random variables at the same time, and we were looking at linear combinations. And when we were evaluating variances associated with linear combinations of variables, the topic of covariance came up. We had this covariance quantity floating around that sometimes increased and sometimes decreased the variance of the linear combination. Now you'll see in today's content that covariance is very closely associated with correlation. They are essentially measuring the same underlying structure in the data. So let's take a look. What we're trying to get at today is measuring linear dependence between variables. So the setup we're going to assume is that we have pairs of random variables. We observe x, y pairs of data. So the x and the y with the same subscript represent measurements taken on the same unit sampled from a population. This could be, for example, measuring someone's shoe size and also their height. Or for a food type, it could be measuring protein content and carbohydrate content. One unit sampled from a population measuring two different quantities on the same unit. And often this is done because it's believed that those two values may be associated with one another. Right, if I know what someone's shoe size is, that gives me some information about how tall they are. It's not a perfect relationship, but if I tell you I'm looking at two people, one of them wears size 5 shoes and one of them wears size 15 shoes, you would expect the one who wears a size 15 shoe to be much taller than the one who wears a size 5 shoe. And often the nature of that relationship is linear. So we are digging in, trying to find ways of quantifying just how strong a linear relationship exists. And we talk about that as a correlation coefficient. You'll often also see this referred to as Pearson's correlation coefficient. Pearson was a British statistician. He did some revolutionary work in terms of figuring out how to quantify the strengths of these relationships. So let's look at how we measure that, firstly, at the population level. So at the population level, the covariance between two variables x and y is defined as their joint expected value minus the expected value of x and the expected value of y. Now, you know how to calculate those individual expected values. But the joint component here, we didn't cover that in class. And I'm not going to ask you to do this calculation. I am just telling you what the formula is. But if this is something that is of interest to you, it's part of the chapter 5 content and in the textbook that we didn't cover. So it's just a formula that relies on having a joint density function or a joint mass function for two variables. And so just to give you a sense of what the flavor is there, remember, if you're calculating an expected value, say expected value of x, you're either integrating out over the real line or you're summing over all possible x values. If you move to 2 dimensions and you're trying to calculate the joint expected value of 2 variables, that means you have to integrate out over 2 dimensions or sum over all x, y values that exist in some real plane. Now, the covariance measure is sometimes difficult to interpret. It can be arbitrarily large depending on what your variable structures look like. And so a standardized version of that is often preferred, something called the correlation coefficient. We represent the correlation coefficient by the Greek symbol rho. And again, if you're calculating this at the population level, you would take the covariance between the 2 variables, and you would then divide by the square root of the variance of x times the variance of y. And the reason the correlation coefficient is preferred is it always lives on the interval -1 to +1 with the endpoints included. So I'm not going to ask you to do these calculations at the population level. This is just for you to understand that there are formulas governing the dynamics that happen at a population level. Our interest will be working at the sample level. So say that you have observed data, right? You have collected XY pairs through some kind of random sampling from the population, and you want to estimate the correlation coefficient. So the sample estimate gets denoted by a lowercase r, and this calculation, we will look at examples of this. This is something I will ask you to do. First, we have to calculate the sample covariance. So this is the sample equivalent of the population calculation on the previous slide. And this is done, you have an initial factor 1 over n minus 1, and you multiply that factor by the sum of the product of the x and the y values. So you multiply each x and y value in a pair and sum over those products, and then you subtract from that the product of the sum of the x's times the sum of the y's over n. And if this formula feels a little bit familiar, if you change the y's to x's and the whole formula is written in terms of x's, it looks like how you calculate the sample variance. So it's a related formula. Now, once you've calculated the sample covariance, you can convert that to a sample correlation. And we do this by taking the sample covariance and dividing by the square root of the product of the sample variances. So you calculate the sample variance for the x data, calculate the sample variance for the y data, multiply those, take square root. The sample correlation coefficient has some good properties. It satisfies the condition that the value be between negative and positive 1. And so it has the same range as the population values. In fact, the sample correlation we consider to be a point estimate for the population correlation, right? So it is our best informed guess as to what the true population correlation is. Now, how does this number work and how do we interpret it? Well, let's think about the example I mentioned earlier, where I was saying, oh, perhaps we're measuring shoe size and perhaps we're measuring height. And if you go and collect data on these two quantities, you might see a figure, if you plot for each individual their shoe size and their height, and you did that for every individual, you would see a scatter cloud of points, perhaps looking something like the figure I just drew here. Now, what you should imagine is if you were to find a straight line or find a linear equation that best follows the trajectory of the cloud of points. In this case, that line would have a positive slope. And so therefore, we would expect a positive correlation value. So the sign of the correlation corresponds to the sign of the slope of the trajectory line that best runs through your data. So it's able to detect whether there is a positive or a negative relationship in the data. And for that, you just look at the sign. You interpret the sign of the correlation. And secondly, we interpret whether the correlation is weak or moderate or strong. And this would be a measure of, again, if you look at this example with shoe size and height, the strength of the relationship is a measure of how closely those points cluster around the line that we drew. Now, there are no absolutes here in terms of how the correlation should be interpreted. The best we're going to do is create a rule of thumb for interpretation in this class. This is not a rule that will always be applicable in all situations. It will guide our interpretation in this class. Anything with a correlation where the absolute value is less than 0.5, we will consider that to be a weak correlation. A moderate correlation will be any time the correlation is 0.5 or larger up to 0.8. And a strong correlation will be any time in absolute value the correlation exceeds 0.8. And remember, absolute value, so we're only looking at the positive side and also can't exceed 1. So if an absolute value, it's between 0 and 0.5, we consider it weak. Between 0.5 and 0.8, it's moderately strong. And larger than 0.8, it's a strong correlation. And I can show you a few examples of what this will look like. Top left figure, we just have a random scatter of points. If we think of this as a representation of pairs of x, y values, right? Random scatter. And so what you would expect, you don't see any evidence of a linear trend. And so if you calculate the sample correlation for this data, you would reasonably expect it to be close to 0. The next figure here, if you imagine a trend line running through the data, the points are clustered pretty closely to that trend line. Because they're clustered pretty closely, we would expect this correlation to be strong. And so in this case, I would guess that this is about a 0.85. Now, I'm not going to ask you to look at a figure and come up with a number like that, but I would expect you to be able to look at that figure and then look at the next one, bottom left, where clearly you can again see a trend line, in this case downward sloping. But if you look at those points, they're a lot more dispersed around that trend line. So firstly, in this case, you would expect the correlation to be negative, and it's not as strong as in the other figure. In this instance, my guess would be this was closer to negative 0.5, so much more of a moderate correlation. And then finally, the last figure here, these points follow a perfect quadratic relationship. Like looking at the figure, no one is going to argue with you that there is a nearly perfect or a perfect relationship between these two variables. But on this figure, if you were to go and calculate the correlation, you would still get something really close to zero, because correlation is a linear measure. It measures how strong the linear component of the relationship is. So it can assess if something can be well approximated by a straight line. For this quadratic curve, there's no way to draw a straight line that fully approximates a big part of the curve. And so because there's no linear equation that's a good approximation there, the correlation is going to be close to zero. There are other instances where you have a nonlinear relationship and you can still end up with a large correlation, but that has to do with being able to draw a straight line through a curve that approximates a big part of that curve well. What you should remember is, for correlation, two components. Calculate the actual number from the data using this formula. Then you can use rules of thumb to interpret that correlation, whether it's positive or negative, and whether it's weak, moderate, or strong. But none of that should be done without looking at a graphical representation of the data to make sure you are actually doing the correct analysis, because you need to be evaluating linearity. Now, all of what we're doing here is underlined by the normal distribution or the bell curve. We are assuming here that the population the data are being obtained from is bivariate normal. And what that means is, if we look at each of the two variables on their own, the x variable follows a normal distribution, the y variable follows a normal distribution, but it also dictates what their joint behavior is. And I'll show you the equation in a moment for the bivariate normal distribution. Now, there is a bit of notation. If we have a random pair x and y, the means or the averages of the two variables are denoted by mu x and mu y. And here you can see why the subscript becomes important, because we have two means to distinguish between. We also denote their variances by sigma x squared and sigma y squared. And finally, the correlation between them is denoted by rho. Having defined that, the joint PDF is governed by this bully of an equation. Now, this equation quantifies both the bell curves for the margins for x on its own and for y on its own, but then also describes how the data structure allows for linearity in relationship. If you could do a top-down view of this curve in 3 dimensions, what you would see, for example, if your correlation were 0.8, you would see these concentric ellipses if you did a top-down view. Whereas if the correlation were 0 and you did a top-down view, you would have perfect circles, because then there's no relationship, no straight line that you can draw through. And the one on the left, of course, you can see how a linear trend can kind of fit through those concentric ellipses. But there's no best direction on the right-hand side for drawing lines through the circles. Now, that being said, our focus here is firstly going to be on calculating the correlation coefficient, but then secondly, it will relate to testing hypotheses about the correlation. So we're going to develop methodology that firstly allows us to test for the absence of correlation, testing whether there is no linear relationship, which is equivalent to rho being equal to 0. So we're developing a testing procedure here for the null hypothesis that the population is assumed to be bivariate normal and has a correlation of 0. And the alternative, as always, can be a complete negation, or it could be a one-sided test statistic, or one-sided rejection region or calculation. The test statistic that we use here we'll call big T, and it's defined as the sample correlation coefficient times the square root of n minus 2 divided by 1 minus the square root of the correlation coefficient. And the reference distribution for this test statistic is a T distribution with n minus 2 degrees of freedom. So we will look at our examples in our live Zoom session at how to test this hypothesis. And to wrap up for today, we're also going to look at how to construct a confidence interval for a population correlation based on sample data. Now, the hypothesis test here is specifically done under the assumption that the correlation is equal to 0. We don't want to have that type of assumption influence us if we're doing a confidence interval. So we're developing methodology assuming that there is a non-zero correlation. Actually, correction, we're first looking at the testing problem, and we'll then convert that to a confidence interval problem. So our first testing procedure was to determine specifically if the correlation is equal to 0. But now we're also going to look at a testing procedure where you specify a non-zero correlation. So you specify a specific value between negative and positive 1 that is not equal to 0. So in this instance, just for notation, I'm going to let big R be a random variable denoting a correlation coefficient. And we convert that to a V scale by taking 1/2 times the natural log of 1 plus R over 1 minus R. This random variable V is approximately normal and has a mean of 1/2 times the natural log of 1 plus rho over 1 minus rho. So it's a function of the underlying population correlation, and it has a variance of 1 over n minus 3. So the testing procedure, if you're testing the null hypothesis that rho is equal to some specified value rho 0 against some alternative, whether it's a two-sided or a one-sided alternative, your test statistic in this case will be a Z statistic, which is given by the V transformation we just did minus 1/2 times the natural log of 1 plus rho 0 over 1 minus rho 0, and all of this divided by 1 over the square root of n minus 3. And if this is the testing procedure that you follow, your reference will be a normal 0-1 distribution, approximately. This is a large sample result. So this does require that your sample size be at least 30 before you can implement this. Of course, we can adapt the same procedure to construct a confidence interval. And the way we do that is we calculate little v. That's the same transformation we've just seen, but using our sample correlation coefficient. We then calculate numbers C1 and C2, defined as v minus z tail value over square root of n minus 3, and v plus that same tail value over square root of n minus 3. And we can then convert this to a confidence interval for the population correlation. And that is given by e to the 2c1 minus 1 over e to the 2c1 plus 1. And the right side is exactly the same transformation, just using C2 instead of C1. And with coverage level 100 times 1 minus alpha %, this is a confidence interval for the population correlation coefficient. And the confidence interval, both the lower bound and the upper bound, also respect the boundaries of what a correlation coefficient can be. So they can never exceed +1 and they can never exceed -1 on the left. We will look at examples of all of these concepts during our next live Zoom session. So I hope you all have a good week, and I will talk to you soon.